Okay, folks, let's get into this XPS thing, X-Ray Photoelectron Spectroscopy. This is a really, really cool technique. As we'll see, the spectrometers for these things are enormous. They're expensive. That's why we don't have any here at Cal Poly Humboldt. But they are very common in material science characterization. So let's go for it. So XPS, or as I said, X-ray photoelectron spectroscopy, is a surface-sensitive technique. So just like was shown in this photoelectric effect picture, where we're shining light at the surface of a material, only electrons will emanate from the very surface of that material. So this is a great way to characterize like the surface of a catalyst, for example. Or really the surface of any solid that we can get under ultra-high vacuum. So this can provide elemental composition analysis, and we can also get molecular analysis when used correctly. And the oxidation state or chemical environment is sensitive to this technique. So that's what allows us to do molecular analysis as well. So specifically with X-ray photoelectron spectroscopy, this is the X-ray is energetic enough to knock out core electrons. So we can do UV photoelectron spectroscopy where we're knocking out valence electrons, but the chemical environment and oxidation state is really sensitive to our core electrons. So by using X-rays as our ionization source, we're really, really sensitive to this chemical environment. So this is a picture of what an XPS might look like. As noted, it is complicated. So this is what's known as our hemispherical energy analyzer. So I'm just going to approximate that and say this is our detector. So our sample would be located in this vacuum chamber right here, and this is our X-ray gun. So X-rays are bombarded on the sample, and photoelectrons are ejected up into this hemispherical energy analyzer. So the electrons come through and are analyzed here. So we can see a better schematic representation of that here in this slide. So again, we've got our photon source, and this could be any number of these types of wavelengths depending on what type of photoelectron spectroscopy we're doing. So as noted, if we're doing an X-ray, then we're doing XPS, but we could also use these other sources of radiation to do a photoelectron spectroscopy technique as well. So our hemispherical energy analyzer, that big dome-looking thing, operates much like a mass spectrometer. So there is a magnetic field in here that will allow electrons to take this curved path, and depending on the time or the curvature that these electrons take, that will allow us to measure their kinetic energy. So recall, we're taking advantage here of the photoelectric effect, which says kinetic energy equals h nu, the energy of incident radiation, minus phi, our binding energy. So we measure this, we know this, and thus the binding energy is determined. So here are some XPS spectra of various metals, and you can see we get peaks corresponding to different orbital levels where those electrons were ejected from. So that is pretty cool. So let's zoom in, or really let's take a look here at a diagram so we can see these dynamics. So when we knock out an electron, we call that photoemission or photoionization. This would be our main, XPS mechanism. So we're measuring the kinetic energy of that electron. However, there's a couple of other things that can happen with this core hole pair that's created. So we've now got this core hole, okay? And an upper lying electron could relax down into that position. And if it does so, that can either cause another electron to become unstable and emitted. So that would be called an Auger electron. So that's a French word, French name. Or we could imagine getting X-ray fluorescence as well. So these processes are what we call secondary, and this process is our primary. So in the case, most of the time, we are interested in the primary photoionization. The secondary can be used as a diagnostic. However, it gets really complicated down there with complicated samples. Okay, the next thing to talk about is spin-orbit splitting in XPS. And we've talked about this in our previous sections, where now we recall when we have an electron revolving around a nucleus, this creates angular momentum on the z-axis given by the right-hand rule. Additionally, that electron is spinning, and that also creates additional angular momentum. So when those two angular momentums are parallel, that gives us the high J value. When they are anti-parallel, so in other words, when the electron is spun down, that gives us the low J value. And as we shall see, because this is a low energy arrangement, it requires more energy to knock the electron out of this state. So this would be a higher binding energy. This would be a lower binding energy, which I know seems counterintuitive, but we'll look at some spectra and flush that out here in a moment. So the binding energy of low J is higher than the high J value, as we just discussed. So the magnitude of spin-orbit splitting increases with nuclear charge. So the larger is our nuclear charge, the bigger there is a difference in the energy between the low J and the high J state. And the magnitude of spin-orbit splitting decreases with distance from the nucleus. So as we go from P to D to F, we see the difference in energy decrease as we get further away from the nucleus. So let's take a look at a couple of simple examples, all simple elements here. And there's a couple things to discuss. So one, we can see here for elemental carbon, we get a nice peak in the vicinity of around 285 electron volt. And notice that there is only one peak. So recall the degeneracy of this will go as 2J plus 1, where J takes on all values L plus S all the way down to L minus S. So in the case of S orbitals, L is equal to 0, and S will be either plus 1 or minus 1. So we don't get any splitting from this S orbital. However, when we look at the 2p or 3d or even 4f, we do see splitting. So recall, for example, with the 2p level, so there we're looking at copper 2p. So that level will get split into the low J value. So that would be the J 1/2, right, where L is 1 and S is minus 1/2. And J is 3/2. That's our high J value. Okay. So I noted earlier that the low J value has the higher binding energy, and that might seem counterintuitive because the low J value is lower in energy, and that's because we have to remember here this technique is relative to ionization. So that's what I'm showing right here at the top of this scale. So as you can see, it would take more energy to remove the J 1/2 value than it does the J 3/2 value. And then, of course, the difference between those two levels is given by the spin-orbit splitting constant. So in the case of copper, the difference between those two is about 19.8 electron volt, which you can see separated in this spectra. And there you can see 2p 1/2, so that corresponds to the low J value. It's got around 954 or so binding energy, whereas the high J value, the 3p half, is more like around 934. So if we look at silver 3D, we can see the binding energy is different. It's not only a different orbital, but it's a different atom. But more or less the trend is preserved, where you can see 2p is much closer to the nucleus than 3D. So this copper 2p is showing up around 950 or so electron volt, but the silver 3D only shows up around 370 or so electron volt. Now I know what you're thinking, well, but carbon's at 285 and it's 1s, it's very close to the nucleus. So we have to compare apples to apples, right? We'd have to compare like the copper 2p to the copper 3D to the copper 4F, for example, if assuming it contains those, which it doesn't. So a better example would be to compare like the silver 2p to 3D, etc. Okay, sorry if that was confusing. So, and then finally, when we get over to the gold, the 4F level, you can see the binding energy has gone way down because those electrons are very easy to remove, and the spin orbit splitting has gotten much less. So if we now look at what some molecules look like, so here's a simple molecule, titanium oxide. And you can see here it's telling us the energy source, 730 electron volt, was the radiation used. So that gets subtracted from the electron kinetic energy, and thus we get the binding energies. So you'll notice here the things at like 1s and 2s are at a much higher binding energy than things like 3s and 3p, which again makes good sense because those 3s and 3p levels are easier to remove. So let's talk about some of these peaks. So again, we noted the core levels have the highest binding energy. There's titanium 2s, there's oxygen 1s. Now we can see spin orbit splitting in the low J and high J value for the titanium 2p. Once we get to titanium 3p, that splitting is present, but it's so close together it's hard to resolve on this scale. And then now we notice there's a whole bunch of other things here. Our Auger peaks that we talked about will show up in this spectra. And then now what you should also notice is the background, or really baseline shape for this, is quite wonky. And that's typically due to inelastically scattered photoelectrons. So there ends up being a lot of stray electrons making it to the detector that are inelastically scattered off of the spectrometer or the vacuum chamber itself. And that just owes to this kind of wonky background shape. So as you might guess, and based on our Spec 1 assignment, spectroscopic deconvolution is an absolute necessity in this technique. And then you might be thinking, this is titanium oxide, so why is there a carbon 1s peak? So typically in XPS, you use a piece of like carbon tape or some kind of graphitic surface to place your sample on. And sometimes we can get electrons emitted from that carbon stage. So that's from the sample stage. So we'll note that there. Almost always some carbon shows up in this technique from the sample stage. So as also noted, the chemical environment is very sensitive to this chemical shift in binding energy. So for example, if we looked at the XP region for silicone, and I didn't note what orbital these are coming from, but all the same, what we can see is when the silicone oxidation state is changed, that is also going to change its binding energy, which kind of makes good sense. And generally, an increase in oxidation state will cause an increase in binding energy because as the oxidation state increases, it becomes more and more difficult to remove that electron. And you can see in the case of the sulfur series, that gives you this really nice linear relationship. As we go up single oxidation states at a time, we get a pretty constant shift in that core level. And then the final thing that I want to talk about is what like an organic molecule might look like in XPS. And so when we look at organics, we typically focus on the carbon and oxygen region, and we try to correlate them with each other. So looking at this polymer right here, we can see that there's a couple different types of oxygen as well as a couple different types of carbon. So for example, the carbon in the ring all shows up here at around 285 wave number, and that will have essentially a lower oxidation state than the oxidized carbon, right? Makes sense. And so you can see that oxidized carbon has a higher binding energy than the aliphatic carbon. And of course, we can also note here that we get these other methyl groups, these other aliphatic carbons, and those are also kind of showing up in close proximity as the carbon in the ring. Additionally, we can look at the oxygen 1s region, and we can see that we've got two different types of oxygen. We've got the ether here, and we've also got the carbonyl. So you can see that those both appear in very close proximity to each other, but they can be resolved with this spectroscopic deconvolution technique. And of course, if you're able to match up XPS with FTIR, that gives you an ultimate characterization. So routinely you see people pairing up XPS and FTIR to quantify unknown things. Okay, folks, we'll uncover this. We'll look through a lot more examples and spectra in our live meeting. I will see you there.